Good morning, everyone. Our project is boosting the efficiency of perovskite solar cells via top surface passivation, and our team is Guihua, Yixuan, and Lulu. I will briefly cover the background, motivation, and our passivation strategies. Then I will introduce the structure, the optoelectronic properties, and finally I will show the improved device performance. Under the pressure of global warming and the depletion of fossil fuels, we urgently need high efficiency and low-cost photovoltaic technologies such as perovskite solar cells. And there is the basic working mechanism of a perovskite solar cell, showing how incident sunlight is absorbed by the perovskite layers to generate electron-hole pairs, which are then separated and transformed through the ETL and HTL to form an external photocurrent. Perovskite solar cells have emerged as one of the most promising photovoltaic technologies, with certified power conversion efficiencies already exceeding 27%. However, their performance is still limited by a high density of defects formed during solution processing. These defects, including undercoordinated PP2+, and highlight ions, weaknesses, and anti-side defects, act as deep and shallow traps. They promote non-radiative recombination and reduce both the open circle voltage and fill factor. Therefore, developing effective defect passivation strategies is essential if we want to further approach the theoretical efficiency limited. In our work, we focus on the top surface of the perovskite layer in the standard structure. The perovskite film is prepared by a conventional spin coating and anti-solvent process, followed by the thermal annealing at 100 degrees Celsius. Then we spin coat a very thin organic layer based on the FPH onto the top surface. This molecule has two key functional units, a hydrogen group and a perfluoro substitute. The molecular depot formed by the p-fluorophenyl ring and the hydrogen group can align at the perovskite interface. The hydrogen end anchors to the perovskite surface, while the F-substitute phenyl ring points out, formed a compact hydrophobic organic capping layer.
To understand how this treatment works, we combined several complementary characterizations. We used a glass cutter to cut the sample into 1.5 and 1.5 centimeter pieces for SEM, AFM, KPFM, XRD, and XPS characterization. For PL measurement, the sample were tested directly without cutting. JV curve testing, however, required the use of intact complete devices. First, the morphology. Cross-section SEM shows that both reference and target devices have a perovskite thickness of about 700 nanometer, with only minute differences in overall staking. However, the top view SEM reveals that the target film has fewer voids and noticeably larger grains, indicating better surface coverage. AFM further confirms a smoother and more uniform top surface, while KPFM mapping shows a more homogeneous surface potential distribution for the target sample. The narrow delta CPT histogram indicates reduced potential fluctuations across grains and grain boundaries, which is consistent with effective defect passivation at the surface. Second, the structure and surface chemistry. XRD shows that the coated film exhibits slightly narrower full width at half maximum of the 110 peak and a higher preference orientation, evidencing enhanced crystallinity and more altered crystal element. XPS gives direct chemical proof of the passivation. On the target film, we observe a distinct CF peak at 687 EV, confirming the presence of the fluorinated molecule on the top surface. In addition, the PB4F and iodide 3D peak shift after treatment, indicating coordination between the hydrogen group and PBI2 species at the surface.
Third, we examined the optoelectronic quality by photolensing. Steady-state PL from glass samples shows a much higher intensity for the target film compared with the reference, and PL mapping exhibits a more uniform spatial distribution. Both features point to a low non-radiative recombination rate and improved film quality of the top surface passivation. Finally, we measured the PV performance. Thanks to the improved morphology, better crystallinity, reduced defect density, and more favorable surface energetics, the device parameters are significantly enhanced. The open circuit voltage and fill factor are both increased, and the champion power conversion efficiency raises from 20.5% to the reference device to 22.99%. For the passivated device, the increased voltage is consistent with reduced non-radiative voltage loss, while the improved fill factor reflects low recombination and serious resistance at the top interface. In summary, by introducing a simple top surface passivation, we are able to improve film coverage and grain uniformity, enhance crystallinity and preferred orientation, chemically passivate PP-related defects at the top surface, homogenize the surface potential, suppress non-radiative recombination, and ultimately boost the PCE by about 2.5 percentage points. This work demonstrates that these molecular passivators at the perovskite interface are powerful routes towards highly efficient and steady perovskite solar cells. Such a top surface passivation strategy could be extended to tandem cells or modules, where surface recombination at the arc interface is even more critical. Okay, that's all about our presentation. Thanks for your attention.